In this second lecture about data handling, let's talk about interpolation. More specifically, let's talk about linear interpolation. I think I'll spend a lot of time discussing linear interpolation and simple extensions called bilinear and trilinear interpolants. I will also introduce a way to interpolate data when there is no continuous representation of the domain, specifically Shepard and Simpson interpolants. And at the end, I will talk about color space and a quick introduction to classic visualization techniques. So jumping in straight to interpolation, like we discussed during our discussion meeting on Tuesday, the data is often available as samples. And let's think about these vertices here representing the sample points, the locations where the data is available. We already talked about different representations of the domain. So there are different cells that together constitute the domain. So here is an example of a edge or a triangle, a tetrahedron, and so on. We know that the data is available only at the vertices of these cells. However, we need a representation of the data in the interior of this cell as well. So this is the standard problem of interpolation. Let's start with an example in 1D. So let's consider a function f which is defined over the real line. As you can see that the function is sampled at integers. So the value at 1 is close to 1, the value at 2 is close to 3, and the value at 3 is about 0.1 or 0.2, and the value at 4 is close to 4. So now what we would like is to find f at 1.75. There are many ways to interpolate and compute the value of f at 1.75. The simplest is called nearest neighbor interpolation, and the way we compute the value of f at 1.75 using nearest neighbor interpolation is by saying that the value of f at 1.75 is equal to the value at the nearest neighbor sample point of 1.75. As simple as that. So we know that the nearest neighbor of 1.75 is 2, and so the value of f at 2 is 3. So which essentially means that f at 1.75 is 3. So if we try to visualize this, what we see is the straight lines that you see in the graph here. So for all values between 0.5 and 1.5, we attach the value at x equal to 1 and so on. So this is called nearest neighbor interpolation, sometimes also called as a piecewise constant function. So f in this case is called a piecewise constant function. The more familiar interpolation is the linear interpolation. So here f is represented as a piecewise linear function. So between two sample points, let's say 1 and 2, we would like to interpolate the value of the function using a straight line. or using a linear function. So the value of f at 1.75 here is given by finding the intersect with this line. So we all know how to compute this f at 1.75 using linear interpolation. Just to make sure that we understand what are the benefits and shortcomings of the two interpolants we have seen so far, the nearest neighbor interpolant is very fast. It doesn't require any arithmetic operations except for a simple rounding operation. On the other hand, the linear interpolation is also not that bad. It is fast. It requires one multiply and a divide operation. The nearest neighbor interpolation leads to discontinuities. So the function has jumps. That's what this means. The linear interpolation, of course, like I said, f is represented as a piecewise linear function, PL function, a piecewise linear function which is continuous. Both the nearest neighbor and the linear interpolation guarantee that the data values are do not go beyond the bounds. So the bounds in both cases are fixed at the extremes of the sample points. This is a nice property, and we will see that some of the other interpolants do not satisfy this property. So what are the other interpolants? Quadratic comes next. So in the case of a linear interpolant, we required two sample points, and we could fit a line passing through these 2 points. In the case of a quadratic interpolant, in order to uniquely determine the interpolant, we need 3 sample points. So we would need the 3 sample points along a line. The line could be, as a special case, the line could be the x-axis. But this could be any line. So let's say that the line is parameterized by t. We have already seen how any line can be represented using a single parameter. Let's think about a straight line that's parameterized by t. And we have the function f sampled at 3 points on this line. So we essentially have 3 equations, 3 variables for a quadratic function on a single variable. So we can solve this to get the interpolant. So you can maybe pause for a second and try to do this for yourself. So what you have is t sub I, f sub I for 3 points, I equal to 1, 2, 3, and you are given a generic point t4, and you would like to find f at this point on the line. Moving on, we would need more sample points in order to do cubic interpolation. For example, here there are 2 points, x1 and x2. So you would clearly need 2 additional points and the function to be sampled at these additional points in order to determine a unique cubic interpolant. An alternate way to define uniquely a cubic interpolant is to sample the function at x1 and x2, but in addition to have an estimate of the slopes at these 2 points x1 and x2. So if you assume that the blue curve here is the cubic interpolant, what we are saying is that we would like an estimate of the tangent at this particular point to the cubic interpolant. So if we have x1 g1, x2 g2, so the two slopes. In addition, if we have x1 f1, x2 f2 as in the value of the function at these 2 points, then we have essentially the same information, and we can use this to uniquely determine a cubic interpolant. Representing using the slopes definitely increases the time for computation. However, it allows us to ensure that the resulting interpolant is continuous with respect to the slopes as well. So so it's clear that the slopes of the adjacent points, so this is, let's say, x1 and x2, and then there is another interpolant that begins with this same x1, so let's say this is x2, and let's say between x1 and x3 we have another cubic interpolant. We know that the slope that is used at x1 is common, and hence the new piecewise cubic interpolant is C1 continuous, as in the slopes are also continuous. This is a nice property to have. There is a special kind of interpolant called the cubic splines. You may look it up if you are interested, or take a class on computer-aided geometric design. The cubic splines ensure that the second derivative is also continuous, as in C2. They belong to the class C2. One drawback of cubic interpolant is that the bounds are not necessarily controlled. So here is an example where this fails miserably. So to read this out, on the x-axis you have time, and on the y-axis you have the percentage of oxygen level measured in some experiment. Now clearly the percentage is a positive non-negative value, and you can see the sample points here marked together with a cubic interpolant. And it's clear that this fails miserably because the interpolant goes below 0. The cubic interpolant has no way of guaranteeing that the values remain above 0. So these considerations are also important when one chooses an appropriate interpolant. So with that note, I think we will stick now to linear interpolants and simple variants of linear interpolants. So let's talk a little bit about linear interpolation in 2D. So here is the interpolant f. F is the piecewise linear function that you obtain by sampling at the different vertices of a triangle mesh. We assign different weights to every vertex wi, and so f at a point in the interior of the triangle is essentially the weighted sum of the function values at the 3 vertices 0, 1 and 2. Now there are many ways in which the triangle can be represented, as we have seen in an earlier class. So the triangle points in the triangle could be represented using 2 parameters, t and s, and so this is essentially parametric coordinates. Any point in the interior of the triangle can be represented as a linear combination or as an interpolation between these 2 vectors. And this can help us determine the weights of the 3 vertices. There is an alternate way to identify weights. This is using something called barycentric coordinates. I ask you to look this up if you are interested. So here is the main idea. A barycenter is something like your center of mass. The barycentric coordinates assigns weights to each vertex that corresponds to its mass or its effect on the object. Now, in this expression, alpha, beta, and gamma are the barycentric coordinates. The properties that the barycentric coordinate satisfies is that alpha, beta, gamma have to be between 0 and 1, and they sum up to 1, right? So more specifically, if you are one of the vertices, let's say P2, then the barycentric coordinate that corresponds to P2, which is gamma here, will be equal to 1, and the barycentric coordinates corresponding to the others will be equal to 0. Of course, if you are at P0, then alpha will be 1 and beta and gamma will be equal to 0. For the center of mass, alpha and beta and gamma are all equal, and in this case 1/3. So any point inside the triangle gets a coordinate, and this coordinate is called the barycentric coordinate. So given the barycentric coordinates, we can use them as weights here in this expression and compute the function at that particular point. So the barycentric coordinates essentially gives us linear interpolation for an unstructured mesh or a triangle mesh. Now when you have a grid, the function f is specified at the grid vertices. So again here we would like to use linear interpolation to the best extent possible. So the way we carry this forward is by attempting to do linear interpolation along each axis, right? So this is not a problem. We have two independent axes, so we interpolate f linearly along each axis. However, if we apply this linear interpolation independently along each axis, we end up with a quadratic function. It so happens that the quadratic function does not have an x squared or a y squared term, but it does have an xy term. And here is the general form of a bilinear interpolant. So this is what is called a bilinear interpolant. So here is an example. If in order to find the value of the function at D, one needs to do 3 linear interpolants. I will let you to work this out, but the idea is that you find the value at D by finding the values first at these locations using linear interpolation along the x-axis, followed by a third linear interpolation along the y-axis. Linear interpolation in 2D extends to 3D as well. So here is the expression for barycentric coordinates, exactly the same as before. Each vertex 0, 1, and 2, and 3 get a weight, and the weights add up to 1. Bilinear interpolation extends to 3D, where you perform linear interpolation along each axis, resulting in a cubic interpolant, which is called trilinear interpolant. As before, this trilinear interpolant is special in the sense that there are no cubic terms. For example, there are no, so here you have 3 axes R, S, and T. As you can see here, there are 3 axes R, S, and T. The cubic interpolant has no R cube, S cube, T cube terms. In fact, it doesn't have any r squared, s squared, and t squared terms. However, it does have rs, rt, and rst terms. So in that sense, so you do have a cubic interpolant. However, it is linear along each axis. I think there is an error here, so this should be 1 minus t. So what this is saying is W7, the weight associated with the vertex 7 is simply RST. So so this is equal to the product of the coordinates that you have. So if you have any point in the interior with coordinates RST, then the weight associated to the point P7 is equal to RST. The weight associated with the point 0 is 1 minus R times 1 minus S times 1 minus T. Now, so far we have assumed that there are linear cells that connect the sample points. What if you have scattered data? How do you interpolate the sample points in this case, right? So let's say we have sample points such as this, and we have a point on the plane where we would like to find the value of the function. Now, of course, this point, the function may not even be defined at this point in certain situations. But let's assume that the scattered data is such that it is a collection of samples on the plane, and the plane is a valid domain. So we would like, we know that the function is defined here, but there is no explicit mesh that is representing the domain. So in this case, so let's call this point again x sub I. Then the value of f, so let's call this just x. The value at this particular point f can again be given as a weighted sum of the value of f at all other points x sub I, right? Shepherd interpolant says that Wi, the weight associated with the ith point, is inversely proportional to the square or the distance or the square of the distance to from the ith point to the point x, right? So it's either the distance or the square of the distance. So essentially what it says is points that are closer to x get a heavier weight as compared to points that are further away. Usually there is a cutoff. So usually there is a cutoff. What that means is that the weight is set to 0 if the distance is greater than some threshold. So such an interpolant is called a shepherd interpolant, and the technical term here is a radial basis function. In this case, we have chosen a squared radial basis function, distance-based radial basis function. So while this approach to interpolate data works reasonably well, there are some idiosyncrasies here. So the value of f is could be determined by all the points in its neighborhood in a biased manner. So for example, this is the same argument that held when we talked about normals. So let's say you have X here and you have multiple sample points, all of which are close to each other and close to X. Now what this means is that these sample points will have together a great influence on the value at X as compared to another sample point here. Now it may so happen that you have sampled the region on the left more dense than on the right, and this sampling density is somehow affecting your interpolation. To avoid this, Simpson interpolant says that you take the point X and you compute the Voronoi diagram of the set of all sample points together with the point X. So I did not talk about Voronoi diagrams in this class. I ask you to look this up because I won't be talking about it in great detail again. So the Voronoi diagram, I'll just give you a quick definition here. The Voronoi diagram is a decomposition of the plane into regions such that every sample point gets a region corresponding to it. So the region associated with this sample point is the set of all points on the plane which are closer to this one point as compared to the others. Right? So that is the definition. So the region would typically look like that, and then you would have something like that, right? So you would, so X will also get a region corresponding to itself, and this will be convex. So these are all the points that are closer to X than any other point. Now, when X was not included, you would get a different Voronoi diagram. So these two Voronoi diagrams are used to compute the value of F. And the way this is done is as follows. So the weight associated, for example, with this point is given by the section of the Voronoi region of, let's say this point is I, and this guy has a Voronoi cell similar to that of X. So this is a polygon. A part of this polygon is eaten up by X. So for example, this guy would have had the Voronoi region of I may have extended till here if X was not included. So the weight associated with I is equal to this pi that is stolen by X from I, right? So this is more indicative of who are the near neighbors and how much they influence X. Right? So this is the idea behind Simpson interpolant. I don't talk about the details here. So if you are interested, I ask you to look it up. Right. So with that quick introduction, let's complete this lecture with a discussion of traditional visualization techniques. So these are traditional or classic techniques that you may have already used or created in your school days and early college days. So I will not talk about them in much detail. For scalar fields, a simple way to visualize is by plotting surfaces such as what is shown here. So here you plot a surface where the elevation of the surface is given by the scalar value at that particular point. Another way to visualize data is via mapping to color using a color map. So different color maps, grayscales such as here, to some single hue based color maps, such blue or red can be used. For visualizing vector fields, there are simple techniques where each vector could be shown as it is. So for example, if the vector is sampled along a grid, then for each sample point, let's say this is a sample point, you have a vector. So the vector can be represented as an oriented line. So that's the vector, and a collection of such oriented lines could be a way to visualize the vector field. This is called a hedgehog. These hedgehogs could be modified into arrows, and then you have oriented glyphs. Streamlines are a way of visualizing vector fields where you integrate these hedgehogs so that you form a continuous curve, and you select the source point and integrate all the vectors that are in this vicinity till they terminate, and that gives you a collection of streamlines. This is an interesting and useful way of visualizing a vector field. So for example, in this picture, what you see is a room, and heat in this room that is modeled as a vector field. So really heat flow. So what you see is that there is there is some kind of a vent on the top that brings in cold air, and then the cold air goes, well, I think this is probably inverted. The color map is inverted. So red corresponds to cool air, and blue corresponds to hot air. So this is your door on the bottom. On the bottom, what you have is the door, and the air comes in and goes into some kind of a stove, which is shown here. That's the stove. Gets hot and then goes up through a chimney out through the exhaust. So the streamline actually shows you the flow of the heat through this room. So streamlines are very useful in showcasing the behavior of the vector field. Interpolation plays an important role when we talk about color. So here are two representations of color. What we have already used, the RGB space. So when we talk about color and its representation using 3 coordinates RGB, we are talking about the color cube, really, right? So we are talking about a point in this color cube which has 3 coordinates, CR, CB, CG, and CB. The color cube is often shown using a hexagon based representation. If you use popular visualization tools, you will see such a hexagon based representation. So this hexagon is essentially just a slice, a planar slice that is orthogonal to the main diagonal, of this color cube. So as you walk along the perimeter of this hexagon, you get the different hues, the different primary colors. A more popular and useful color space is the HSV color space. Here again, you have 3 coordinates that go from 0 to 1. The first coordinate is hue. This actually gives you the true tint of the color, so such as cyan, magenta, blue, and so on. The second coordinate tells you the saturation of that tint. So is it a strong color, so dark blue versus light blue for s equal to 0, and anywhere in between. The third coordinate value tells you how bright the light is, how much white is present in the light. So the third coordinate equal to 1 corresponds to white, and v equal to 0 corresponds to black. HSV is perceptually a more appropriate color space and is often used to represent color maps. So with that, we will end this initial discussion on the data preparation and visualization, kind of introduction to the visualization pipeline. From the next lecture onwards, we will talk about specific techniques for scalar field visualization.